Hello and welcome to weekly physics and technology news headlines with me, your host, Dr. Jacob Hughes.
Yes! Yes!
Today's date is August 6, 2024, and I'm going to be talking all about stars, supernova, type 1a and type 2 supernova.
This is unreal.
And T Coronae Borealis.
I'm so stoked.
It's going to be a blast. Hi. This video provides valuable educational content about stars. I'll explain the star cycle and supernovas clearly and try to make it fun as normal.
Terrific!
The topic is relevant at any time. However, if you're watching between August and December 2024, it will align with news and scientific articles on T Coronae Borealis making headlines during this period. In today's discussion of physics and technology news headlines, I will discuss the star cycle, binary stars, type 1 and type 2 supernovas, as well as the exciting news that T Coronae Borealis, a binary star located about 3,000 light-years from Earth, is expected to soon brighten dramatically, signaling a recurring nova which is similar to a type 1a supernova. Now, this is 3,000 light-years away, so it actually happened 3,000 years ago. So it's actually ancient history. If it did happen at all, we'll find out soon. To begin with, we need to understand the life cycle of a star. The star cycle begins with a cloud of gas and dust known as a stellar nebula, which is primarily composed of hydrogen. These nebulas are massive, beyond our comprehension.
So much hydrogen.
When a shock wave travels through space, it causes the nebula to collapse. Gravity pulls the hydrogen together, forming stars of various sizes. Our sun is only average, but it's good to be average because if our sun was massive, we wouldn't enjoy life. Once a star forms, it starts its life. Hooray! In the main sequence, burning hydrogen. For a star like our sun, this phase lasts about 12 billion years. When the hydrogen runs out, it begins to fuse helium into carbon, releasing even more energy. This energy causes the star's outer layer to expand and cool, transforming into a red giant. The star can grow up to 200 times the sun's diameter. The intense luminosity drives away the outer layer, creating a stellar wind that can eject more than half of the mass of the star. The ejected outer layers form a planetary nebula. Eventually, what remains is the core, now a small, hot, but faint object known as a white dwarf. If the star is a massive star, not just an average star like our sun, then after the red giant phase, you get a massive explosion known as a supernova, and what's left over is a neutron star or a black hole, and I'm going to discuss the star cycle in a little more detail in the next few slides. On this slide, I have some actual pictures from NASA of a stellar nebula and a planetary nebula. This is the famous Pillars of Creation stellar nebula. So this is where the star would start from.
Amazing.
You go back here,
Wow.
This is a stellar nebula, and this is an actual stellar nebula, and this is about 5 light-years tall. So this is one big puppy. Over here is a planetary nebula, and if you recall, a planetary nebula is this portion of the star's life. This picture was taken by NASA's Spitzer Space Telescope. Nebula is Latin for the word cloud. I took 4 years of Spanish in high school and never used it since, but nube is Spanish for cloud, and I think that sounds better than nebula. On this slide, I have a picture of a star in its main sequence. Our sun is an example of a star in its main sequence.
It's a hydrogen
At
fiesta.
the center of the star is the core, and in the core, there's a fusion reaction. There are 4 protons fusing together to make a helium nucleus. And because of Einstein's equation, E equals mc squared, this releases a vast amount of energy. This is known as the proton cycle. This is well documented on many sites on the internet. If you're interested in this, I recommend you look into it. For example, Wikipedia is a good source. At the center of the star is like many hydrogen bombs going off. That creates a large outward pressure. And that large outward pressure is what we call the radiation pressure. The reason the star doesn't just blow up and disappear is because there's an inward pressure from gravity. These stars are very large, and so the stars are in equilibrium. The center of the star has hydrogen fusing to helium. There's an outward pressure, this radiation pressure, and there's an inward force of gravity, and so the stars are in equilibrium. By the way, it's interesting to know that a photon of light that starts at this point takes about 1,000, sometimes even 1,000,000 years to get from this location in the star to this location in the star. And then once it leaves the star, it takes about 8 minutes to get to Earth. So when you get hit with a photon of light, that photon of light was probably 1,000,000 years old. Now let's discuss the next phase of the star's life, the helium flash and the red giant. When stars up to about 2.25 solar masses run out of hydrogen, they begin fusing helium in a process called the helium flash. This releases a large amount of energy, which is absorbed by the surrounding layer. Helium flash lasts about a minute and releases the energy of about 10 to the 23rd of the largest nuclear bombs on Earth. After that minute or so is over, the red giant phase begins. The star's core fuses helium while its outer layers expand and are expelled slowly. This phase lasts for millions of years, which is actually a short amount of time compared to the lifetime of the star. When the core's helium is exhausted, it contracts again. Stars like the Sun are not massive enough to fuse carbon or oxygen. What's left over is a planetary nebula and then a white dwarf. For larger stars, once helium fusion is complete, hydrogen begins to fuse into carbon, then carbon into neon, neon into oxygen, and finally oxygen into iron. Iron has the highest binding energy per nucleon as shown on the binding energy chart on the left.
Tickle me and call me Elmo. This is amazing.
Once a star reaches iron with atomic number 56, it's like being the person who thinks they can pull the lowest brick on a Jenga tower and being wrong. Gravity takes over and the star collapses rapidly in a spectacular explosion called a supernova. During this explosion, other elements are formed through endothermic nuclear reactions which require energy. This picture is a real picture of a supernova, 1987A. At this point here, you can see a star which is not remarkable. It's just like all the other stars in the sky. But then when that star exploded, the star was so bright that it took over all the other stars in the sky just for a short amount of time, but that's what a supernova explosion looks like. It has an unbelievable amount of energy. We're almost ready to talk about the exciting news involving T Coronae Borealis. But first, I need to briefly tell you about binary stars and type 1a supernovas. This is an animation from the NASA website, and this is an animation of a binary star. So what is a binary star? A binary star system is just a system of two stars that rotate about each other. That's what a binary star is. Our sun is a single star, and again, that's good. If our sun was a binary star, that would make our life a lot less fun. A binary star system is two stars that rotate about their common center of mass. So for example, this is an animation of a binary star. There's one star here and there's another star here. The stars are different sizes, of course. They're not going to be the same size. And these two stars are rotating about their common center of mass. And that's what a binary star system is. And for the final part of the video, I'm going to talk about type 1a supernovas and T Coronae Borealis. For this portion of the video, I wrote a script and I'm going to have an AI voice read it. I like the way the AI voice sounds, and it's also me getting in touch with my feminine side. Here's an animation from NASA Scientific Visualization Studio of a type 1a supernova.
A type 1a supernova occurs in a binary star system where a white dwarf accretes material from its companion star. When the white dwarf accumulates enough mass, it reaches a critical point and undergoes a thermonuclear explosion, resulting in a supernova.
In a type 1a supernova, the white dwarf explodes and it's destroyed. It's blown to smithereens after the explosion. But in a recurring nova, that's not the case. The white dwarf remains and the process just continues, and in this case, it continues every 80 years.
Scientists expect that before 2025, a star called T Coronae Borealis, or T Cor-Bor, will undergo a significant event. T Cor-Bor is a binary system composed of a huge red giant and a tiny white dwarf. Despite its small size, the white dwarf is extremely dense and hot, with a fierce gravitational attraction. The white dwarf in T Cor-Bor is slowly drawing hydrogen and other gases off the red giant, accumulating the material on its surface. Eventually, enough material will gather for the immense gravity to fuse the hydrogen, causing a thermonuclear explosion. This explosion will make the ordinarily dim star, barely visible through binoculars, flare to naked eye brightness, despite being 3,000 light-years from Earth. The star will emit upwards of 100,000 times the sun's annual energy output in an instant, making it a significant event. However, this explosion isn't powerful enough to destroy the white dwarf. Instead, the star will fade over the days and weeks following the explosion and eventually return to its usual brightness. This cycle repeats roughly every 80 years, making it a predictably recurrent event. This is why astronomers are excited about T Cor-Bor's imminent explosion. This event is called a nova, which is a smaller version of a supernova. Historical records and observations show that T Cor-Bor has undergone nova events approximately every 80 years, with the last recorded event occurring in 1946. This pattern suggests the next event is imminent, possibly before 2025. If you see this in the news headlines, then hopefully you will understand more about what is being talked about. And if you watch this video after 2025, then hopefully you will learn something about the star cycle and Type 1a and Type 2 supernovas. Thank you for watching, and please subscribe to the YouTube channel of Dr. Jacob Hudis.
Acephysics.org. Math and Physics Tutoring with Dr. H. Acephysics.org. Math and Physics Tutoring with Dr. Hudis.